So in this example, we've got a similar situation. It's another city with a population at time t years. After a certain date, that population increases at a rate proportional to the population at that time. So again, we have to construct and solve a differential equation and also sketch. So again, we can see we've got P and T, which are both going to be positive because we're looking at time. Time's always increasing, and this population is increasing. So the rate of change of the population with respect to time is proportional to the population at a particular time. Okay, so that's the proportional part, and it's just population. In the last example, it was the square root of the population. Now remember, we can replace that proportional sign with an equal sign and a k, and because it's increasing, our k here is positive, so this is going up. Okay, positive rate of change. Now what we need to do is we need to solve this dE, or differential equation. So let's do a bit of swapping. dP equals kp, bring the dt up, and let's bring the p underneath. And now we're going to integrate both sides. So we've got the integral of, I'm just going to expand this and write it as 1 over p instead of dp on p, put the dp there, equals the integral of k dt. Now k is a constant, which means that when we integrate this side, we are going to have log of p. Now I'm not going to use the modulus signs because I'm just going to state here that p is positive, so I don't need to use them. Integrating this side will be kt plus a constant, and now because this was dp dt, we're going to solve for p. So let's raise everything to the exponential, so to the power of e. The e and the log cancel out, and this side is interesting because you've now got e to the kt and the plus e to the c as two things that are multiplied together. So when you have an addition in a power of an exponential, you're really multiplying these two things together. Now e to the c, we can call that a constant, and so I'm just going to call that p naught. Oops. So e to the c equals p naught, and it's just called p naught, it's our initial p, because when t equals 0, p equals p naught, which is a constant. So that's our initial population, p naught. Alright, so our differential equation, let's go through what we needed to show, and I'll put a little box around them. So construct an appropriate differential equation, that's the differential equation constructed. Solve it, so we've done that here. We've solved the differential equation, and now our last job is to sketch it. So I'm just going to pick up this section, put it on the next page, and then we can sketch what this looks like. So put some axes down. Now because we're looking at positive time and a positive population, this is time and this is population p, we only need to be in quadrant 1. And we know that when t equals 0, y-intercept, or in this case p-intercept, is at the point p0. And this particular graph is exponential in nature, so it will go up like that. Okay, and you might want to give another point as well. So we know when t equals 0, p equals p naught. You might want to do maybe like t equals 1, and then you'd have p equals p naught e. E to the k, like that. So if you want to show a couple of points, that's cool. That's p naught e to the k right there. So you've got, in terms of its type of graph, it's exponential, and it's positive exponential population growth for this graph. So that's the solution, the graph, and the differential equation for this situation where the population increases at a rate proportional to the population at that time.